Light is amazing. It's energy that travels in waves. These waves are disturbances in electric and magnetic fields, hence the name electromagnetic waves. Light is everywhere. It allows us to see the world around us. Think about the colors of a rainbow or the sparkle of a diamond. These phenomena are all thanks to the way light interacts with matter. Optics, the study of light, helps us understand these interactions. Understanding how light behaves at different surfaces is crucial in many fields. These fields include photography, telecommunications, and astronomy. Let's dive into the fascinating world of optics and explore two fundamental phenomena: reflection and refraction. Reflection is something we experience every day. Look in a mirror and you see your reflection. That's because light bounces off the smooth surface. When light hits a surface, some of it bounces back. This is reflection. The angle at which it hits the surface is the angle of incidence. The angle at which it bounces off is the angle of reflection. The law of reflection states that these two angles are always equal. This simple law governs how we see ourselves in mirrors and how light bounces off any smooth surface. Reflection is essential for many technologies. Mirrors and telescopes help us see distant stars. Reflective materials are used in road signs for better visibility at night. Refraction is the bending of light. It happens when light travels from one medium to another. A medium is anything that light can travel through. Air, water, and glass are all examples of media. Imagine a straw in a glass of water. The straw appears bent at the water's surface. This illusion is due to refraction. Light travels at different speeds in different media. When light travels from air to water, it slows down. This change in speed causes the light to bend. The angle of bending depends on the angle at which the light hits the surface, and the refractive index of the two media. Refraction is responsible for many optical phenomena. It's why eyeglasses can correct vision, and why a prism can split white light into a spectrum of colors. Section 4, Fresnel equations, predicting light's path. Now let's talk about how much light is reflected and refracted. The Fresnel equations, named after French physicist Augustin Jean Fresnel, give us the answer. These equations may sound intimidating, but they describe a simple concept. The amount of light reflected and refracted at an interface depends on the angle of incidence and the polarization of light. Polarization refers to the direction of the electric field in the light wave. Light can be polarized, meaning its electric field vibrates in a specific direction. Unpolarized light has electric fields vibrating in random directions. The Fresnel equations are essential for understanding and designing optical instruments. They are used in various fields, including photography, telecommunications, and laser technology. Section 5, the curious case of the Brewster angle. At a specific angle of incidence, something interesting happens. All reflected light becomes completely polarized. This angle is called the Brewster angle, named after Scottish physicist Sir David Brewster. The Brewster angle occurs when the reflected and refracted rays are perpendicular to each other. At this angle, the reflected light has no component of the electric field oscillating in the plane of incidence. The Brewster angle has many practical applications. Polarizing sunglasses use this principle to reduce glare from reflected sunlight. It is also used in photography to reduce reflections from surfaces like water and glass. Section 6. Optics in action from cameras to communication. The principles of reflection, refraction, and the Brewster angle are not just theoretical concepts. They have numerous practical applications that impact our daily lives. Cameras use lenses that rely on refraction to focus light onto a sensor. This allows us to capture sharp images of the world around us. Fiber optic cables, the backbone of modern communication, use total internal reflection to transmit data over long distances at incredible speeds. Polarizing filters in photography, inspired by the Brewster angle, reduce glare and enhance colors in photographs. Liquid crystal displays, or LCDs, found in televisions, smartphones, and computer monitors also utilize polarization to control the transmission of light. The study of optics continues to drive innovation in various fields. From developing new imaging techniques in medicine to advancing communication technologies, the principles of light interaction with matter are fundamental to our technological progress.